Hi guys, so today we're going to look back at some more graphing with a new type of function, and these are called piecewise functions. Now what a piecewise function is, it's basically how we would write an equation for the graphs that we looked at last class, because these graphs are just going to be little bits and pieces of different functions. So an example of the way a piecewise function looks is on example 1. So you see f of x, which we know is a function, and then you see that bracket with 3 different functions, and each of those functions has a different interval. So the way that this is read, it tells us that this graph is going to look like the graph y equals 3x on the interval when x is less than -2. This graph is going to look like x cubed in between the x values of -2 and 3, and this graph is going to look like y equals -3 when x is greater than or equal to 3. So the first thing we're going to do is we're just going to evaluate it. Okay, so if I want to evaluate f of -4, I need to figure out which of those 3 intervals makes the most sense. Well, -4 is going to be less than -2. So because that's the interval where that falls, I'm going to use the 3x function to evaluate it. I replace x with -4, and I get -12. All right, if I look at f of -2, well, this top function is only when x is less than -2. It's not less than or equal to. Because I need to know when it equals -2, I need to drop to this middle function, and I need to use x cubed. So I plug in -2 for x, and I get -8. All right, f of 0. f of 0 is going to be in between -2 and 3, so it falls on that second function as well. So 0 cubed is 0. And then f of 3, I can't use that middle function because it's not equal to 3, it's only when x is less than 3. X is greater than or equal to 3 when y is -3. I don't even need to do any math there, there's no x's, it's just -3. All right, so same idea, but we're going to use a graph. So this graph is an example of what a piecewise function looks like. It's one linear function here, it's another linear function here, and it's a constant line over there. So to evaluate f of -1, this is what we did like last class. When x is -1, the y value is 0. f of 2, when x is 2, y is 1. f of 1, when x is 1, y is 1. I use the filled in circle, okay? I don't use the open circle because it's not actually equal at the open circle. f of -2, so here's the x value of -2, there's the filled in circle. So f of -2 is -1. Then finally f of 0 is 1. When x is 0, y is 1. So that's how we'd evaluate on a graph. So we're actually going to graph some of these, and this is going to kind of review what some of our parent functions look like. So it's important to understand what your different parent functions are. And in fact, I'm actually going to skip ahead and come back here. And let's go ahead and fill in our parent functions just in case we don't remember them, because it can be really important to know these. So first of all, the linear parent function would be f of x is equal to x. That is just a straight diagonal line through the origin. Some of the points it goes through, 1, 1, 0, 0, 2, 2, -1, -1. All right, very simple. Absolute value is the one most commonly remembered. That's the absolute value of x. It's absolute value, so it looks like a v. Okay. Some of the points that it goes through are, again, 0, 0, and 1, 1. But -1, +1, and then 2, 2, -2, +2. Because remember, absolute value means we take, if it's a negative, it becomes positive. It's just saying the value of it away from 0. Quadratic would be x squared, and that is our parabola shape. It goes through 0, 0, 1, 1, -1, 1, -2, 4. Sorry, +2, 4, and -2, 4. All right, those are the ones that are most commonly remembered. The ones we tend to have the most trouble with are these ones. So cubic is x cubed. So again, goes through 0, 0, 1, 1, and -1, -1. But because we are cubing x, If I were to plug in 2, I would get 8. If I were to plug in -2, I would get -8. So that's actually going to be off my graph, but you can helps you to see the shape, how it kind of curves as it goes through there. All right, square root. That one looks a little bit different because there are no negative x values unless we do a transformation. So it starts at 0, 0. Then it goes to 1, 1, 4, 2. And it keeps going in that direction. Cube root does continue in the negative direction because it's possible to have the cube root of a negative number. So -1, -1 is again a point on this graph. But what makes it different from the cubic function is instead of going through 2, 8, it goes through 8, 2, because the cube root of 8 is 2. And it goes through -8, -2. So again, we're a little bit off our graph, but you can still see what that shape looks like. All right, rational, it's been a while since we've done that one. That one is 1 over x. That's the parent function. Now, we didn't do a lot of transformations to the rational parent function, but the biggest thing to remember from that rational function is that it had asymptotes. This graph has a vertical asymptote at x equals 0, because you can't divide by 0, and it had a horizontal asymptote at y equals 0, because it was bottom heavy. It also goes through 1, 1, and -1, -1, and it just goes towards those asymptotes. Exponential and log are the two most recent that we did, and again, we got to make sure we can tell these two apart. Exponential is the base to the x power. Okay, so I'm going to just go ahead, for the sake of graphing, I'm going to go ahead and graph 2 to the x, just because it's a little bit easier to see the points. Remember, exponential has a horizontal asymptote at y equals 0. All right, and then it goes through 0, 1, because anything to the 0 power is 1, and it goes through 1, comma, the base. So in this case, I'm graphing 2 to the x, so it's going to go through 0, 1, and 1, 2. It also would go through -1, 1 over 2. The log function, so it's log base b of x, that's the inverse of exponential. So what I'm going to go ahead and graph is log base 2 of x. This one has a vertical asymptote. That's the biggest difference between them. It goes through 1, 0, and then base, comma, 1. And since I'm graphing log base 2, I'll make it go here. And that's your log parent function. So it's important for us to be familiar with these parent functions as we do piecewise. These are also just going to be important just for your math classes going forward to know what these shapes look like. You'll learn some new parent functions next year in pre-cal. Let's go ahead and draw these graphs. So this first one, x plus 2 squared plus 1, that is a parabola. We know that that parabola has been shifted left 2 and up 1. That's where the vertex would be. But we are only graphing this parabola when x is less than -2. So what I'm going to do is I'm going to go ahead and make an open circle, and I'm going to plug in -2 for x, and that's going to be my starting point. So if I plug in -2, I get 0 squared plus 1. So -2, 1 is an open circle on my graph. I know that this graph is going to be a parabola. I know this graph is going to have a vertex of -2, 1 because it's been shifted left 2 and up 1. So that open circle is actually the vertex of this parabola. If you want to get some other points, you can plug in other x values, but I'm only going to graph when x is less than -2, which means I'm only going to graph to the left of that open circle. So if I plugged in -3, -3 plus 2 would be -1 squared is 1, 1 plus 1 is 2. Okay, if I were to plug in -5 or -4, okay, that would give me 4 plus 1, which is 5. And again, I'm only going to graph in that direction. Okay, remember, if you don't remember the parent function or things about it, you could plug in those points to get those values. But it helps to know the parent function so we know the general shape that this should look like. All right, when x is greater than -2, I'm graphing a line. That line has a slope of 1/2. That line has a y-intercept of -1. So in order to graph that line, I'm going to cross at -1. I'm going to go up 1 and right 2, up 1 and right 2. and then down 1 and left 2. But I'm going to make an open circle at that point because it says x is greater than -2. Okay, it does not say equal to. So this is what your piecewise function would look like. All right, let's go ahead and look at B. So I'm going to graph the line x minus 2 when x is less than -1. So what I'm going to do is I'm going to go ahead and plug in that starting point. So I'm going to go ahead and plug in -1. -1 minus 2 is -3. So -1, -3 is going to be an open circle on my graph. Then to the left of that point, I am graphing the line x minus 2. That has a slope of 1, which means I'm going up 1 over 1, and I'm going in the opposite direction. All right, in between -1 and 2, I am graphing an absolute value function with 2 transformations. It's been reflected and shifted down 3. So absolute value, I'm shifting the vertex down 3, and then I'm also reflecting it. So instead of going up, this graph is going to be going down. And that should be a closed circle. And then at 2, that's going to be an open circle. Again, if you want to get those points, if I plug in -1, the absolute value of -1 is a positive 1, but then I make it negative. -1 minus 3 is -4, which is the point that I filled in with the closed circle. If I plug in 2, the negative absolute value of 2 minus 3, that's -2 minus 3, which is -5. So I should have plotted the point to -5, which is where my open circle is. Right. Then finally, this graph is a quadratic when x is greater than or equal to 2. So the first point I'm going to plot, I'm going to plug in 2. 2 squared is 4. That's going to be a closed circle. And this one's hard because the graph is not quite big enough. But x squared is a parabola. The vertex is at 0, 0. So this graph is actually going to continue up that way. I don't want to make that look like the vertex. It's going to continue up, curved like that. So just remember, if I were to have the whole graph, it would have been there. But I don't need that orange part because I'm only graphing where it's greater than 2. All right, so let's look at C. So when x is less than -3, I'm graphing the line y equals 5. Y equals 5 is just a horizontal line at 5. So I go to the x value of -3. It's going to be an open circle. And I'm going everything that is less than. Between -3 and 2, I'm graphing the parabola x squared minus 4. That has been shifted down 4. So the vertex is down 4. Right? To get the 2 endpoints of that parabola, I'm going to go ahead and plug in those values. So I'm going to go ahead and plug in -3. If I do -3 squared minus 4, I get 5. So -3, 5 is going to be a point on my graph. It's going to be a closed circle. So if you notice, we already put an open circle there. That's okay. That closed circle is basically going to fill in that open circle that was already there, and those 2 pieces are going to meet. If you want some more points to make this more specific, go ahead and plug them in. If I plug in 1, I would be at 1, -3. And if I plugged in -2, I'd be at 0. So I'm going to go ahead and connect those. If I plug in 1, 1 squared minus 4. And then if I plug in 2, 2 squared minus 4. And that is going to be an open circle. So again, at 2, that's where it stops. That's where my open circle is. And the last one is a square root function. Okay, square root function that's been shifted to the right 2. So the square root function right 2, remember, square root function looks like this. It has a clear defined starting point. That starting point is actually going to be at 2, which is where that open circle already is. If I plug in 2, 2 minus 2 is 0. The square root of 0 is 0. Okay, and then just continue that square root pattern over to the right. So this whole thing actually in this case, sometimes with piecewise functions, very similar to the ones we did last class, they're all connected because all those open circles are actually filled in by the previous graph. The last piecewise function we're going to look at is a little bit different because it doesn't have less than or greater than symbols. It has equal and not equal symbols. So what this one means, it says it is going to be this function when x is not equal to 2. That is every single place on my graph except for one spot. So the first thing we're going to do is we're going to look and see what that graph looks like. X squared minus 4 over x minus 2 is a rational function. If I were to factor that, we're going to see exactly what it's going to look like because the x minus 2 cancels out. And if you guys remember, if it factor cancels, that's going to create a hole in your graph. So this graph is going to have a hole when x equals 2. Okay, that hole is going to be at 2. If I wanted to get the y-coordinate, I took 2 and I plugged it in. 2 plus 2 would give me 4. So this top graph is going to be the line x plus 2 with a hole at 2. And we know there's a hole at 2 because it also says x is not equal to 2. So there's going to be a hole at 2, 4. And then everywhere else, it is just the line x plus 2. Now, what the second part is telling me is basically that I'm going to fill in the hole. So this is telling me if x equals 2, then y equals 3. So in that one spot, when x equals 2, I'm actually going to have a hole, a dot filled in down there. Now what that means for us, it's telling us that this graph is not continuous. If that value was something other than 3, if that value actually was 4, this graph actually would be continuous, even though it has that hole there, because that part right there would fill in the hole. But it's in a different spot in this case. All right, so the last thing we're going to do, this is going to be where it's really important to remember your parent functions and what they look like. We're going to write the equation for the graph. So what we're going to do here is we're first going to figure out what the function is. So I'm going to have that bracket, and we'll look at this first interval. So this is a horizontal line. So that function would just be y equals 3. Then we're going to list where that happens. So that happens when x is less than -1. Not or equal to, because it's an open circle. All right, then we go to the middle section. The middle section is a parabola. To write the equation, we need to see how it's transformed. It has been shifted up 1, and that's it. So that parabola is x squared plus 1. The plus 1 is outside because, again, it's gone up. Where that's happening, it's in between -1 and 2. -1, it's or equal to, so I put the bar underneath it. Then the last one is a line. I just need to write the equation of that line. In order to write the equation of the line, we need a slope and a y-intercept. So the slope is negative, and then I'm going down 1, right 1. So -1. Then the y-intercept, if you can't see, we just need to think if this graph continued, my y-intercept would be 4. That's happening for all x values greater than or equal to 2. All right, then my last one, again, really important to remember our parent functions. It's hard to see what this first graph is if we don't know our parent functions. That first section, that is a square root graph, but it's been reflected. So since it's been reflected, okay, it's been reflected over the y-axis, which means I need a negative inside the square root. And that is happening for all values when x is less than 0. Not or equal to because it's an open circle. Then I look at the middle, okay? That's a quadratic. It's been shifted to the right 2 and down 3. So I would make that x minus 2 squared minus 3. That's how I show those two transformations. Then I list the interval. It happens from the x value of 0 until the x value of 3. And because it's closed circles on both ends, both of those are or equal to. Then finally, the last one has a y value of -1. That's it. It's just y equals -1, horizontal line, and that is when x is greater than 3 for all values. And that's it for piecewise functions. So again, piecewise functions, really make sure you know your parent functions, know how to apply those transformations, and then all we need to include then is the interval where that's happening.